immediately. So how do we find vertical asymptotes for rational functions? And the theorem is very simple. It just says that all you have to do is let zeros of the denominator. Okay. Now there is a little catch here, and the catch is that you have to make sure that the rational function is in lowest terms. In other words, if the top and the bottom have a common factor, you need to simplify first. In our case, we didn't have to do it in the first example because there was no common factor between top and bottom. So let me write this down. So let's suppose that we have a rational function. Now this is specific to rational functions, okay? So let r of x equals p over q be a rational function, and then assume that r of x is in lowest terms. So what I mean by this is that p and q have no common factor. So p and q have no common factors. So if they have, you need to simplify before you use this theorem. Have no common factors. Then the function r has a vertical asymptote, okay, x equals c, if and only if c is a zero of the bottom. If and only if c is a zero of q of x. So that means that you know that once you have a rational function in lowest terms, the zeros is the denominator. When you get close to those numbers, the function is going to go to positive or negative infinity. Okay, so you have yourself a vertical asymptote. So you can find them very easily. Well, as easy as it is to find the zeros at the bottom, which this could be complicated, as you know. Okay, but then when it comes to graphing, you will have to do what we were doing earlier. Okay, play with the sign and see if it's positive or negative infinity, so you know if it goes down or if it goes up and that kind of stuff. All right, so let's see. Let's do an example. So finding vertical asymptote. Yes, the zeros at the bottom are vertical asymptote, but you have to make sure that it's in lowest terms. So you have to be careful. Okay, you have to be careful. So in this in this example, let's do the following. Let us find domain and the vertical asymptote. Okay, and let's see. Let's put some functions here. Let's do f of x equals 4x plus 3 over 3x minus 1. Then let's do r of x equals x minus 4 over 3x squared plus 5x minus 2. And then let's analyze g of x equals x squared minus 9 over x squared plus 4x minus 21. Okay, so here we have some functions. Let's go ahead and let's find the domain and let's find the vertical asymptote. I'm going to do the first one. I'm going to let you work on 2 and 3, and then we do it together. Okay? So let's see. Remember, here it's very important to have the zeros at the bottom. So zeros at the bottom. So that would be 3x minus 1 equals 0. So that makes x equals 1 over 3. So that means that what's the domain? So the domain would be all real numbers except 1 over 3, as we saw. So that's the domain. And then vertical asymptote, because this is already in lowest term, is the line x equal 1 over 3. Okay? Using the theorem, our function is already in lowest term. There is no common factor between top and bottom. So the vertical asymptote is just the line x equals 1 over 3. So go ahead and figure out domain and vertical asymptote for 2 and 3. I'm going to give you, say, 3 minutes to work on this, and then we're going to do it together. And again, use the theorem.
Are you going to show us how to graph it too? Or?
Yes, but first you need to learn how to find the asymptotes.
Okay.
Okay. So go ahead and find the asymptotes of these functions. The vertical asymptote. We still need to talk about horizontal. Once we know both vertical and horizontal, then we are ready to graph. Okay? Which basically, you know, what we just discussed, it should be able to graph a function, but we're gonna take this slowly, one step at a time. Okay, so right now just do this example. Find the domain and find the asymptotes. I'm gonna give you 3 minutes. Okay, so let's see. What do you think is very helpful to do first to analyze this? You should first factor everything. If you factor everything, it's very easy then to answer these questions. Okay. So let's go ahead and let's factor everything. Can anybody tell me how to factor the denominator for number 2? Okay, but if the zeros are rational, that means that we can factor this easily. So let's see. Honey found 2 zeros, right? -2 and 1/3. So that should tell you that 3x plus 1, 3x minus 1 is a factor, and x plus 2 is also a factor. Maybe. Let's see. Let's factor this. How do you factor 3x squared plus 5x minus 2? So we can do this, 2, 1, and then put a negative here. Exactly. So 6 minus 1 is 5. So we have 3x minus 1 and x plus 2, right? And why is it good to factor? Well, because if you factor the denominator, then you can see everything there. So it's very easy to see what the zeros are. It's also very easy to see what the vertical asymptotes are, which are the same as the zeros. Anyways, you need to check that you don't have a common factor between the two. So everything works out nicely if you factor everything first. So whenever you're going to analyze a rational function, you should do this first, factor everything. Okay? All right, so let's write the zeros at the bottom. So what are the zeros at the bottom? Those are going to be 1/3 and -2. Okay, so what's the domain for this function? Is all real numbers except these two guys. So it will be -infinity to -2 union -2 to 1/3 union 1/3 to infinity. That's our domain. And then how about vertical asymptotes? Do we have any common factor between top and bottom? There is no common factor, so be careful. So remember, when you write vertical asymptote, don't just write the numbers, because it's supposed to be the equation of a line. So here it's important to write x equals -2 and x equals 1/3. Okay, if you write the numbers only, that's not a line. So here you need to write the equation of a vertical line. All right, good. Questions about number 2? Yes, Maria?
So when I wrote the domain, I wrote from -infinity to -2, then u, and then from 1/3 to infinity. I didn't write like the middle part.
And what about the middle part? Remember, all we have to do is skip 1/3 and -2. But if you avoid the middle part, then you are skipping all the numbers that are in between.
Oh, okay.
Right? Remember, all we have to do is remove 1/3 and -2 from the domain. Everything else is part of the domain.
Okay, got it.
So using interval notation, this is how it looks. If it gets you a little bit confused how to write it from here, my advice is do the following: draw a picture. Here is -2. Here is 1/3. You just want to get rid of these two guys, but everything else is okay. So if you draw this, then you will see that you will need 3 pieces. And each of the pieces are the ones that we have here. Does that make sense?
Yeah, thank you.
Okay, good. All right, so for the next one, again, let's go ahead and let's factor everything first. So top, x plus 3, x minus 3. The bottom, two numbers whose product is -21, and the sum is 4. That will be 7 and -3. So x plus 7, x minus 3. So remember, the sum has to be +4. So it will be +7 and -3. Okay, good. So now I know that when you see this, you may be tempted to simplify, but please don't do so yet, okay? Because if you simplify, you're gonna get the domain wrong. Remember, the original function is this one. So to find the domain, you need to use the original expression. This function is not defined at 3. If you simplify, you're going to get something that will be defined at 3, and then you will get the wrong domain. Okay? So when it comes to domain, you need to use the original expression. So still, I'm going to write zeros at the bottom of our function. So at the bottom are going to be -7 and +3. Okay? And therefore, what will be the domain? The domain is everything except these two numbers. Here is -7, here is 3. You don't want these two guys, everything else. Okay? So the domain is -infinity to -7 union -7 to 3 union 3 to infinity. Now for the vertical asymptote. Now remember, if you want to use theorem, you have to make sure that the function is in lowest term. So for purposes of the vertical asymptote, now we go ahead and we simplify and we write this blue function. But you need to understand that this equality is valid as long as we assume that x is different than 3. Because if x is equal to 3, the blue function is okay. It will give you an output. The our function is not going to give you an output because it's not defined. Okay? Very good, honey. That means that there will be a hole. When we graph, we're going to have a hole at that point. Very good. Very good. So, but why is it that we are simplifying? Well, because if we want to look at the vertical asymptote, we need to make sure that our function is in lowest terms. So x equal 3 is not really an asymptote, as your classmate is pointed out, Han is pointing out, is actually a hole. We're going to see that when we actually start graphing. Okay, so what is it that we have left? The only zero that we have left that's not a hole is -7. So we have one vertical asymptote, namely x is -7. Again, x equal 3 is not good here for vertical asymptote because it was also a factor in the top. So they cancel each other out. Okay? And to find vertical asymptote, you need to make sure that you have your function in lowest terms. Okay, questions? Questions? In finding vertical asymptotes of a rational function? Okay, so if there are no questions, then let's continue. Let me do one more quickly. How about this one? Let's write h of x equals x cubed over x squared plus 1. All right, so, and oh, by the way, here we don't care about complex zeros, okay? We are only looking at real zeros because remember our goal is to graph these functions, okay? So we are only looking at real numbers now for the purpose of graphing anyways. So what's going on here? What are the zeros at the bottom? Do we have any real zeros? So be careful. The zeros at the bottom will be plus or minus I, right? Notice that the denominator is x squared plus 1, right? So that means that this has no real zeros because the zeros are plus or minus I. Everybody okay with this? So what does this mean in terms of the domain? What will be the domain of this function? The domain is all real numbers, okay? So you can plug in whatever you want. Well, Sarah, there is domain. It means that everything is fine, okay?
Why is it plus or minus I?
Okay, solve the equation. Was x squared plus 1 equal to 0? That would be x squared equals -1, and then when you take square root, you get x is plus or minus square root of -1, right?
Oh yeah, true.
So that would be plus or minus I. So Maria, what you are talking about is if you had x squared minus 1. If we had x squared minus 1, then that would factor what you're saying, and then the zeros would be plus or minus 1. But that's not what's happening here. We have x squared plus 1. x squared plus 1. If you want to factor that, you need to use complex numbers. It will be plus or minus I, x plus I, x minus I, if you want. Okay, but again, the point is that this doesn't have real zeros. Therefore, there are no asymptotes for this function. Okay, and there are no problems. The domain is all real numbers. You can plug in whatever you want. Okay, vertical asymptotes, none. So this example is here just to show you that there could be rational functions that don't have vertical asymptotes. Here is an example. Okay, so think about it. So Sarah, think about it. What's the domain of a rational function? It's all real numbers except those that make the denominator equal to 0. If there is no denominator, if there is no real number making the denominator equal to 0, then every real number is okay. So the domain will be from negative infinity to positive infinity. So this is a way of saying all real numbers. Remember, this is interval notation. This means all real numbers. Okay, this means all real numbers. Anything is good. You can plug in whatever you want into this function. So again, that little example here was to show you that sometimes you don't have vertical asymptotes. Okay. All right. So now that we understand how to find vertical asymptote, is basically just a question of finding zeros at the bottom, really, making sure that it is in lowest terms, and then you find the zeros at the bottom and you're good. So if you can find zeros, you can find vertical asymptote. Then let us now talk about how to find horizontal asymptotes in general. And something that maybe some of you did not see in college algebra, there is another type of asymptote that functions have, that rational function have, a slant asymptotes, okay? So we have to have a little chat on slant asymptotes as well. All right, but we will see that in the examples. Okay, so again, remember, the question about horizontal and slant asymptote is always a question about end behavior, okay? Both of them, they deal with this notion of end behavior. Whenever you talk about the end behavior of a rational function, what you're really asking is, do we have a horizontal or do we have an slant asymptote? Okay, and they are actually mutually exclusive. You either have one or the other, but not both. So the general question that we are asking here is, what is the end behavior of a rational function? What is the end behavior of a rational function? We did one example at the beginning today. Okay, so let's see. In other words, what we are asking is, given a rational function, as x approaches positive infinity, what could we say about r? And when x approaches negative infinity, what could we say about? So how do we do this kind of stuff? All right. So let us analyze. We're going to analyze 3 examples, and from these 3 examples, we're going to hopefully draw some conclusions. Okay. All right. So the first one will be function like this: f of x equals 3x minus 2 over 5x squared minus 7x plus 1. This is kind of similar to the example that we opened up today, okay, in the sense that we have a range of polynomials where the degree of the top is less than the bottom, okay? And so you can think of this as saying, oh, well, when x is very big, the bottom is going to grow faster because the leading term is an x squared, and therefore this is going to get small. But let us actually see this algebraically in one shot. I'm going to go ahead and divide everything by x squared, okay? So since x is very big, remember, end behavior, so we are away from 0, so nobody can stop you from doing this. It's okay to divide top and bottom by x squared. Why x squared? Because that's the highest power that I'm seeing, okay? So we're going to get a red function. That would be 3 over x minus 2 over x squared over 5 minus 7 over x plus 1 over x squared. And just like what happened earlier in our first example today, when x is very big, what can we say about all of these terms? All of these terms that have an x in the bottom, they will go to 0 because they will get very small. So this is gonna get close to 0 on top, 0 minus 0, over 5 in the bottom. So this is equal to 0. So moral of the story, for this function, when x approaches positive infinity, f of x approaches 0. When x approaches negative infinity, f of x is going to approach 0. In other words, we found also horizontal asymptote, the line y equals 0. Okay, questions on this first example? It's very similar to the first one that we did today. Any questions on this one?
I have a quick question.
Yes.
So when I was doing the homework, you know how like there's sometimes videos to help you with the homework?
Yes.
In one of the videos, the guy was like saying that if the degree of the denominator is higher than the numerator,
Yes.
then it's always the horizontal asymptote is always going to equal y equals 0. Is that true?
Yeah, of course. That's what we're trying to lead towards to. Like I said, we're gonna do 3 examples, and then hopefully we're gonna draw some conclusions out of those examples, and then we're gonna write the statement. So what you're seeing here is actually the reason why that statement that they were saying in the video is true, right? Because if the degree of the bottom is bigger, what you can always do is divide top and bottom by that bigger power, and this will always happen, that you will get 0 on top and then a number in the bottom. So at the end of the day, your function is going to get close to 0 when x is very big. Does that make sense?
Yep.
So again, I'm going to be writing down those theorems, but we need to go through this process first so you understand where this is coming from. I just don't want you to take those things for granted. So that's why we are here, to question these ideas. Yes, Maria. Maria, do you have a question?
Oh, sorry. Yeah. Can you hear me?
Yes.
So when we're dividing everything by x squared, we're assuming that x is bigger than 0?
Different than 0. Let me put it here. Different than 0. Because remember, we are approaching positive and negative infinity. So, it could be negative, but we are very far away from 0. And that's the only thing that we should concern ourselves, because when you divide by x, you have to be careful, because if x could be 0, then, you're getting into trouble. You cannot divide by 0.
But how do you know that 3 over x and minus 2 over x squared, it's approaching 0?
Oh, because x is approaching infinity. So again, remember, what is it that we are analyzing? We are analyzing behavior, right? So here we are analyzing what happens when x is very big. That's what the arrow means. So when x is big, then the arrow is telling me that those little terms are approaching that number that I'm writing. So when x is big, 3 over x gets small, and 2 over x squared also gets small, and so on.
Okay, thank you.
No problem. Okay, so, and again, the bottom line is what your classmate said earlier, that we're going to see that whenever we have a function like this, if the degree of the top is less than the bottom, that's it. This will always happen. So you're going to have y equals 0 horizontal asymptote. Okay? That's one of the conclusions that we're going to draw once we're done with these examples. Okay, let's keep going. Actually, let me also show you something else. So remark, we can also use something, some people like to call this like the garbage rule, okay? And you're gonna see what I mean by that. All right, so we have 3x minus 2 over 5x squared minus 7x plus 1. So remember that after all, the top and bottom are polynomials, right? And the end behavior of a polynomial is given by its leading term. So it makes sense to say that when you have this rational function, the end behavior is going to be given by the ratio of the leading terms. Because anyways, is whatever happens on top over whatever happens in the bottom. So we can say that this is going to be approximated to 3x over 5x squared. In other words, when you ignore the lower degree terms. This approximation is, of course, as long as x is very big. When x approaches positive or negative infinity, the lower degree terms, they really don't matter for the function, okay? So our function will behave just like this quotient. But now this is 3 over 5x, and you can clearly see that this approaches 0 when x approaches positive or negative infinity. Okay, so that would be a quicker way of seeing that instead of having to divide top and bottom by all of those terms. Did you guys understand this? Some people talk about this as the garbage rule because, you know, the lower degree term, that's like garbage, so you just ignore it. What matters is the ratio of the leading terms. Are you okay with this? All right. So let's see. This we can use this then to do another example a little bit faster. So how about this one? X squared minus 9 over x squared plus 4x minus 21. So using this same approach, again, remember we are analyzing m behavior, okay? So we can say that this function is about the same as x squared over x squared. Again, the lower degree terms, they don't matter. And remember, this approximation means as x approaches positive or negative infinity, when x is big. When x is small, of course, these two things are very different from each other. Okay, but the bigger x gets, the closer these two expressions will become, and this is just one. Okay, and in this case, we can see. Let's actually make this a little bit more interesting. So let's put a 3 here and a 4 here. So in that case, we're gonna have 3 and 4, and then notice that here we're gonna get 3 over 4. So we don't have, okay, so I changed it a little bit. I changed it to 3 over 4 to see this leading coefficient business. But yeah, before it was y equals 1, because it was 1 over 1. So as you can see, what we see is that if the degrees are the same, what's going to happen? Because it behaves just like the ratio of the leading terms, the x's, they cancel out. In this case, the x squared cancel out, and you are left with the ratio of the leading coefficients. So from here, we will get that the horizontal asymptote is y equals 3 over 4. So, yes, Marie, question?
Oh no, sorry, I just left my hand raised.
Okay. So as what's the end behavior? When x approaches positive or negative infinity, our function approaches 3 over 4, which in this case, this means, as I draw above, that that's a horizontal asymptote. This is our, the end behavior of the function. And notice that here, this 3 over 4, what is it? Is the ratio of the leading coefficients. And this will always be the case if the degrees are the same, because that means that when you write the ratio of the leading terms, the x's to whatever power you have, the degree, that will cancel out, and you will be left over with the ratio of the leading coefficients. Okay? All right. Questions? Questions for this? So far we have, if the degree of the top is less than the bottom, then you will have y equals 0 as horizontal asymptote. If the degree of the top is equal to the bottom, then the horizontal asymptote is going to be the ratio of the leading coefficients. Now let us do an example in which degree of the top is bigger than the bottom. So for example, what if you have 3x to the 4 minus x squared over x cubed minus x squared plus 1? Imagine that you have something like this. Okay? So if you want to figure out the end behavior, then you can still use the garbage rule very quickly. We can see that as x approaches positive or negative infinity, this is close to this quotient, which would be dx. Okay, so in other words, this function is going to look more and more linear as x gets very big. That's what this means. So in particular, what do we know about 3x? What's the end behavior? 3x is a line like this. So the end behavior is this way. Okay, So for the end behavior, when x approaches positive infinity, I want you to tell me what happens to g, and when x approaches negative infinity, I want you to tell me what happens to g. So what is it? When x approaches positive infinity, what can we say about the function g? What does it approach to? Are you sure? Think about it. We have our function gets close to 3x, right? That's what symbol right here means. That our function is very close to the function 3x when x is very big. So if x approaches positive infinity, what does our function approaches to? It will approach positive infinity because that's what 3x approaches to. Look at the picture that I did on the right. Remember, you guys know polynomials, so you can use that knowledge. And when x approaches negative infinity, what does g approaches to? It will approach negative infinity. Okay, so this is the end behavior. However, is it really the line 3x that we're getting close to? Or is it 3x plus or minus something? So whenever you get close to a line, we say that line is going to be a slant asymptote. But now, very good, Han. So the question is it really 3x or is it 3x plus or minus something? So for that, we're going to do division, okay? So let's do a little division quickly to figure this out. We're going to see that in this case, when the degree of the top is 1 more than the bottom, you're going to have a slant asymptote, okay? It's no longer a horizontal asymptote. There is no horizontal asymptote here because the function is not getting close to a number. As you can see, this means no horizontal asymptote. To have a horizontal asymptote, these guys have to be a number. Okay? So no horizontal asymptote, but maybe we're getting close. It looks like we're getting close to some line. Is it really 3x? Because we just did a quick estimate by using the garbage rule. But maybe we're getting close to something more specific. So to figure this out, we need to do division. Okay? So far we have an approximation. So here is the idea. So note, we may try to improve the approximation that we initially gave. So we may try to improve the approximation. What approximation? We did the approximation that g was about 3x when x is very big, okay? For absolute value of x large. That means positive or negative infinity, okay? So to do this, we're gonna be using division. So to answer this, so to do this, we need to divide. So let's say that we call this one P, and let's say that this is Q. We're gonna divide P divided by Q, okay? So in this case, we're gonna do long division. So let's see, what was our Q? It was x cubed minus x squared plus 1. Then you will see why. It will be clear why this is gonna work. All right, so let's see. Let's do division. So this is gonna be 3x as predicted. Of course, the leading term has to be the same. So then here we're gonna get minus 3x cubed plus 3x. We subtract. These guys cancel, so as positive. So we're gonna get 3x cubed minus x squared minus 3x. And then notice that we can keep dividing. So we have plus 3. So this is gonna be 3x cubed minus 3x squared plus 3. And so this shouldn't be an x here. This should be just plus, no, yeah, 3x there. Okay, then we subtract, then these guys cancel out, and then we're gonna get negative x squared plus 3x squared, so we get 2x squared, and then minus 3x minus 3 is positive. Positive. So why am I putting positive here? So 3x, that's positive, then negative, then positive. That's good. So then when you change the sign, that becomes negative. Yes. So this right here is going to be negative. Okay. All right. So we get 2x squared minus 3x minus 3. And because the degree here is less, this is the remainder. This is the remainder. And this right here is a quotient. And what do we know when we do division? Why is it that we're doing this? So what we know is that if you do p over q, which is really our function, right? That's p over q. What is this equal to? This is always equal to quotient plus remainder over divisor, right? That's what we know when we do this, right? So when we do the division, and now let us analyze our function. So what does this get close to when x is big, when x approaches positive and negative infinity? Well, notice that that fraction that we have here now, the remainder of a divisor, this is going to go to 0 because the degree of the top is less than the bottom. So when x is very big, our function is going to get close to 3x plus 3. So this is a better approximation. It's not really 3x, but 3x plus 3. This guy, we call it the slant or oblique asymptote. Okay? In other words, to find an slant asymptote, all you have to do is do long division. So divide the two polynomials and the quotient is your slant asymptote. The slant asymptote. Let's see. So the function h of x. So wait, what was the letter that we used? G. So the function g, it has no horizontal asymptote, but it has a slant asymptote. Has a slant asymptote, namely y equals 3x plus 3. Okay, so that means when x is big, we're getting closer and closer to this line. Okay, so we're gonna see what that means when we start graphing. So when we come on Thursday, we're gonna actually graph these three functions that all of these functions that we analyzed today with the asymptote. We're gonna sketch the picture of these guys. Okay, any questions on how to find the slant asymptote? Did you understand this?
Is there a way to tell that, like, just by looking at the problem, is there a way to tell that the equation has a slant asymptote?
You can tell that it has a slant asymptote. Yes, look at it. The degree of the top is one more than the bottom. Whenever that happens, you know that there is a slant asymptote. Now, which one is it? No, which one is it? You have to do long. Let's see. Let me remind you what we were doing last time. So remember, last time we discussed vertical asymptotes, okay, of rational functions, and the bottom line was that to find the vertical asymptote of a rational function, all you have to do is worry about the zeros in the denominator, and but the first thing is that you need to make sure that your function is in lowest terms, okay? So you need to simplify any common factor that show up, and then whatever is left, you find the zeros in the bottom, and those are your vertical asymptote. And regarding horizontal and slant asymptotes, in other words, the end behavior of a rational function, what we did was some examples, and then the pattern that we saw is that if the degree of the top is less than the bottom, then it seems to be that there is a horizontal asymptote, and it is the x-axis, the line y equals 0, and when the degree of the top is the same as the degree of the bottom, then there is also horizontal asymptote, but this time is the ratio of the leading coefficients. For example, in this example, it was 3 over 4, because those are the leading coefficient, because you have the same degree between the top and the bottom. And then we did another example in which the degree of the top was bigger than the bottom, but this time the top is 1 more than the bottom, okay? So we saw that this function looks more or less like the function 3x, so there is no horizontal asymptote because the behavior is infinity on one side and negative infinity on the other. However, because it looks like a linear function, then that means that it has a horizontal slant asymptote. But to find precisely what this is 3x is just a rough approximation. If you want to find a better approximation, what we needed to do was divide the two polynomials. And by doing the division, you look at the quotient, and then you can see what the slant asymptote is, which in this case was 3x plus 3. So all of these observations that we did last time in the examples, we're gonna put them all together, and this is actually a theorem. What we observe here is actually always the case. And I have that written down here also just to save time. So let's just go over this statement, but again, this is just a summary of what we discussed last time. So this is about the end behavior of a rational function. So suppose that you have a rational function. In other words, it has a form p over q, where the top p is a polynomial. I'm reading the polynomial, the expanded form. And what I want to pay attention, I want you to pay attention to this is the leading coefficient, which is a, and the degree of the top, which is n. And then the bottom q is again another polynomial, and pay attention to the coefficient. Let's call it b, the leading coefficient, and the degree is m. Okay, so that's how any rational function looks like, a quotient of two polynomials. Then what we realized in regards to this business of end behavior was the following. It all has to do with the degree. If the degree of the top, which is given by n, is less than the bottom, which is given by m, then that means that we're going to have a horizontal asymptote, and that's the line y equals 0. That's the first statement. Now, what if instead we have that the degrees are the same, degree of the top is the same as the bottom, then we still have a horizontal asymptote. It's going to be the line y equals a over b. That's the ratio of the leading coefficients. Okay, those are the ratio of the numbers that are in front of the variable with highest power for each of them. So in cases 1 or 2, so when the degree of the top is less than or equal to the bottom, we are having a horizontal asymptote. Otherwise, if the degree of the top is bigger than the bottom, there is no horizontal asymptote. But what we realized was that if the top is 1 more than the bottom, meaning if n is m plus 1, so the degree of the top is 1 more than the bottom, then we are going to have a slant asymptote, okay? And this is a line, so we have an equation, kx plus c. I'm using k instead of m because m is already taken for something else to talk about degrees. And what is it that we do to find this slant asymptote? We divide, okay? So we divide p and q, and then the quotient will give you the equation of the asymptote. That's the summary of what we did last time. And then the thing that remains to say is what happens if n is greater than m plus 1, meaning the degree of the top is way bigger than the bottom. It's more than 1 than the bottom. Like, I don't know, degree 5 on top and degree 3 in the bottom. Or degree 20 on top and degree 7 in the bottom. When the degree of the top is more than the bottom by more than 1, then what's going to happen is that we can use the garbage rule that we discussed last time. And so our function will approximate the ratio of the leading terms, and when you simplify, you're going to get a power function, okay? And so the end behavior of our function will be the same as the end behavior of this power function. Remember that it depends on the degree. If the degree of this power function is even, then the end behavior will be, parabolic end behavior like this. If the degree is odd, then the behavior will be, like an odd power function. It all depends on what is this n minus m, whether it is an even or an odd number. But the point is that there is no horizontal or slant asymptote in that case. So we have this sort of behavior for the end of our graph. Okay, anyways, questions about this summary. Now we're going to do more examples. But questions about this summary that we have here. Okay, if there are no questions, then let's go ahead and look at some examples. So I'm going to give you some functions, and let us find all the asymptotes, okay? Vertical, horizontal, slant, or whatever there is to be found, let's find it. And, and also let me make a remark. Notice that the cases here 1, 2, and 3, they are mutually exclusive. Okay, it's either one or the other, but not two of those cannot happen at the same time. Okay, so what that means is that if you have a horizontal asymptote if a function has a horizontal asymptote, then there is no slant. Okay, and also, if there is a slant asymptote, that means there is no horizontal asymptote. So it's one or the other, because it has to do with the degrees, and these are exclusive cases. That's just a little comment there. Okay, anyways, let's do some examples. So examples. And this is about finding asymptotes. So find all asymptotes. Let's see. For the first one, let's do f of x equals 8 over x squared plus 4x plus 4. Okay, so remember, the first thing that we should do to answer this question is always factor as much as you can, so we can answer quickly the question. So in this case, the top, there is nothing to do. In the bottom, we can factor this. This would be x plus 2 squared. All right, so let's see. Vertical asymptote. Do we have any vertical asymptote here? So we need to answer vertical asymptote, horizontal asymptote, and then slant. Do we have any vertical asymptote for this function?
Is it x minus, or x is -2?
X equals -2. Very good. So remember, vertical asymptote, those are the zeros of the denominator, right? So here we have 1 0 is -2. You have to make sure that it's in lowest terms. In this case, it is. So you're good to go. X equals -2. Good. Do we have any horizontal asymptote?
Y equals 0.
Y equals 0. Very good. Degree of the top is less than the bottom. The degree of the top is 0. Degree of the bottom is 2. So we have horizontal asymptote, y equals 0. Do we have any slant asymptote for this function? There is no slant asymptote. So no. All right, good. Let's see. Let's keep practicing this. How about, so you should be able to answer these questions fairly quickly. Once you have polynomial factored out and everything, the top and the bottom, then it should be easy to see. Okay, so let's see. We have this. Let's take a look at it. Can we factor the top? At least, can we do this in an easy way? So b squared is 25. So two numbers whose product is 4, and the sum is 5. Okay, so it will be 4 and 1, right? So we should be able to factor this easily. Let's see. What can we do here? -4x, and then put an x here, and -1 and 1. So that's 4 plus 1, that's 5. Okay, so this is -4x plus 1 times x minus 1. Again, here for the purpose of the question, it was not really necessary because what we're about to say right now, but just in case, it's always good to make it a habit and then factor the top, because you will need that when it comes to graphing anyways. All right, so let's see. Let us answer the questions now. So vertical asymptote, horizontal asymptotes, and slant. What's going on here? Do we have vertical asymptote? And if we do, which one is it? Or what are they? Vertical asymptote. So remember, vertical asymptote is x equals something, okay? All right, so if you get complex number, that means that there is no vertical asymptote, right? So remember, that we're not talking about complex numbers here. We are graphing we want to graph in the xy plane. So here, everything is about real numbers now. Okay? Remember that the whole point here is so we can come up with a picture of this thing. So vertical asymptote, those are the real solutions of the denominator. Now there are no real zeros in the denominator, so there are none. This function doesn't have any vertical asymptote. Does everybody understand this? All right, no vertical asymptote here. How about horizontal asymptote? Do we have any horizontal asymptote? Y equals -4. Very good. So notice that the degrees are the same. So according to a theorem, if the ratio of the leading, the coefficient of the top is -4, the coefficient of the bottom is 1. So that would be -4/1, which is just, -4. So y equals -4. Okay, good. And how about slant? Do we have any slant asymptote? No slant asymptote. No. Okay. Questions? Are we okay with this so far? All right, I will assume that we are okay. Let's see. P of x equals 3x minus 1 over 2x plus 7. Let us analyze this one. So let's figure out vertical asymptote, horizontal asymptote, and slant. Let's see. Vertical asymptote, that would be the zero of the bottoms. That would be the line x equals -7 over 2. Then how about horizontal asymptote? Do we have horizontal asymptote here? 3/2, very good. Degrees are the same, so it's 3/2. And how about slant? Do we have any slant asymptote? So we don't have any slant. Good. And then let's see. How about this one? G of x equals -2x squared minus 3x plus 7 over x plus 3. All right, so let's see. Two numbers whose product is -14 and the sum is -3. There is no way that we can find those numbers, so we won't be able to factor these in a straightforward way, so I won't even try. So the point is that, in particular, -3 is not a zero of the top, so the top and bottom here have no common factor. So we don't have to worry about factoring here for asymptote purposes. And let's try to answer then the question: vertical, horizontal, and slant. Let's see, do we have vertical asymptote here for the function g? Yes, we do. So remember, don't give a number. You have to give an equation, okay? So x equals -3 as a vertical asymptote. If you give a number, that's wrong, because you need to give me the equation of a line. Okay? Horizontal asymptote. Do we have a horizontal asymptote here? No horizontal asymptote. Good. Do we have a slant asymptote? So in this case, we do have a slant asymptote. Remember, you have a slant asymptote when the degree of the top is 1 more than the bottom. That's the case here. So be careful, Maria. So remember, to be able to come up with the slant asymptote, what do we need to do? We have to do division, right? So very good, -2x plus 3. So let's see, let's go ahead and let's do it quickly. We can do the division here quickly. Yeah, you need to divide top with the bottom, but because the bottom here is x plus 3, we can do it the quick way. We can do synthetic division, okay? So I'm gonna do the division quickly using synthetic division. Let's see, we're gonna have here -2. So what is this? 6. Then we get 3. Then there's gonna be -9. So it's gonna be -2. So this right here is a remainder, but remember, we don't care about the remainder. What we care about is the quotient. So from here we get that the quotient of the division is gonna be negative 2x plus 3. So what is the equation of our slant asymptote? Y equals negative 2x plus 3. Remember, the quotient of the division, that's the equation of the slant asymptote. You could do long division or you could do synthetic division, which is quicker. But remember, synthetic division is only when the denominator, the divisor, has this form, x plus a number or x minus a number. Otherwise, you will have to do long division like we did in the previous example in last class. Okay, questions?
Professor, number 2, what was the horizontal asymptote?
In number 2, negative 4, y equals negative 4.
Isn't it 1?
No. Why will it be 1?
Well, I mean, y equals 1 over 4?
Now remember, it is the ratio of the leading coefficient. What's the leading coefficient of the top?
Negative 4.
And the leading coefficient of the bottom?
Oh, that's right. You find the ratio. Yeah.
All right, so it will be negative 4 over 1, which is negative 4.
Oh, true. Okay, yeah. Thank you.
Okay, no problem. All right, so are we good in finding asymptotes? All right, so now let us do the following. For these same problems, for these 4 examples that we did here, those for which we found horizontal. So first of all, vertical asymptotes, those are forbidden for the graph to cross. Like the graph cannot cross a vertical asymptote because, you know, those are coming from 0 to the denominator, so the function is not defined. Remember, the idea is that when you get close to this line, the graph of the function goes to either positive or negative infinity. That's what being a vertical asymptote means. However, horizontal or slant asymptote, our functions could cross these lines, okay? Because what they mean is that when x is very big in the positive or negative direction, when x approaches positive or negative infinity, we're getting close to this line. But when x is small, we could be doing all stuff and we could be crossing the lines, okay? So that's not really a problem. So that's also something that you need to worry about when you're graphing rational functions. If you have a horizontal or a slant asymptote, you need to be able to determine if our graph, if our function is going to cross these lines. So let's see, something happened. Okay, so it looks like the connection might come out for a second. Can you guys hear me? Can you guys hear me now? Because it looks like my computer, the connection is coming and going. Can you hear me now?
Yes.
Okay. I don't know. I thought that I went out for a second. Okay. Anyways, let's do the example that I was mentioning. So, example, let us determine from the above functions and where is it that the graph will cross the horizontal or slant asymptote, if any. So, determine for the above functions the point or points, maybe it's more than one, if any, at which the graph crosses the horizontal or slant asymptote. Vertical asymptote, we don't have to worry about it because we will never cross the vertical asymptote. But horizontal or slant, we may, so we need to see. Okay, so let us try to figure this out. All right, so let's look at the first example. So the first one was, what did we use? We use f for that. So we have f of x equals 8 over x squared plus 4x plus 4. And then we found that we had a horizontal asymptote here, namely the line y equals 0. Okay? So the question is, and there is no slant asymptote. So the question is, are we ever going to cross this line? So in general, how is it that you answer this question? How is it that you check whether two functions intersects or not? How do you check for two graphing crossing each other? Anybody? For example, when you have two lines, how do you check whether two lines, if you're given two lines, how do you check whether they cross or not? That's one way of checking. Do you understand the question that I'm asking? Okay, but what point? But what would that tell you? So again, this is the general question that I'm asking. If you're, let's say that you're given two lines, I don't know, the line 3x plus 5 and the line 7x minus 20. And I want to know if these two lines will cross each other. How will you answer this question? When you graph these two lines, you would like to know whether they will cross or not. How do you answer this question? Do you understand the question that I'm asking? Okay, graphing them. But what if you have something complicated? So you could graph, yes, that's true. But what if you have something that's a little bit more complicated that doesn't seem to be, that may not be too friendly to graph? Like for example, we haven't even talked about graphing rational functions yet. Okay, table values, evaluating them. But for this, you need to have some values. First of all, table of values, you can only do finitely many values, right? You cannot sit there. What if the point of intersection is, I don't know, at 3 million or something? Okay, guys, what does it mean for two graphs cross each other? It means that they have to have a point in common, right? So very good, Hannah. So you just set the equations equal to each other and then you solve. So if the two lines are gonna cross, it's because there is an x and there is a y that works for both of them. That means there is a point that works for both of them. So the y is the same. So we just set 3x equals 7x minus 20, and then we solve. For example, in this particular case, what do we get? We're gonna have minus 25. So these two lines are gonna cross at a point whose x value is 25 over 4. I don't think you were going to guess this by using a table of values. So you have to solve an equation. Do you understand this? You just set them equal to each other and then you figure it out, because by setting them equal to each other, you're saying that they have a point in common. You just want to find that point. Of course, in the case of lines, you could have used another clever argument. You could say, well, look, the slope here is 3, the slope here is 7, because the slopes are different. These lines are not parallel. And in the particular case of lines, you know that if two lines are either parallel or not. If they are not parallel, then they will cross at some point. Like one line will go this way, and then the other one will go this way. So they will eventually cross. But this is special for lines. But in general, this is what you do. If you have two functions and you want to see where they cross or not, just set them equal to each other, and then you solve. Okay? So Sarah, we just figured out that the point that they have in common has x coordinate 25 over 4 by solving this equation. We just set them equal to each other. Then if you want to know the y, just plug it in whichever is your favorite equation, and then you will know the y. So if you put 25 over 4 in the first line, you will get the same y than if you put it in the second line. That's exactly what we're just solving here. Do you understand this? All right, so that's what we have to do. So because we have, after all, we have two functions, right? We have a rational function and we have a line, the horizontal line. So if we want to see where they cross or not, what do? we set them equal to each other, and then we try to solve the equation that we obtain. Remember that here f of x is just y, okay? So if you want to know whether the function will intersect the horizontal asymptote or not, all you have to do is set them equal to each other. So we take a rational function and we put it equal to 0 because that's a horizontal asymptote, and then we try to figure out if there is any solution here. Let's see. Is there a solution to this equation? Here we have a fraction equal to 0. Remember, a fraction is 0 only when the top is 0, right? But here the top is 8. So what can we say here? There is no solution, right? There is no way that that expression will ever be 0. The only way that a fraction can be 0 is when the top is 0. Another way to look at it is, you can move this guy over here, multiplying, and you multiply by 0, it's gone. So you get 8 equals 0, which makes no sense. Everybody okay with this? Do you understand that this equation has no solution? All right, so then what's the conclusion here? Because there is no solution, what that means is that they will never cross, right? Hence, f will not cross the horizontal asymptote y equals 0. Will never cross this line. Questions about this first example? Do you understand what we did? Okay, so now let's analyze the next one. So out of x. So we have out of x, which is negative 4x squared plus 5x minus 1 over x squared plus 2. And then we found that we had a horizontal asymptote, and that was the line y equals negative 4. If we want to figure out whether we're going to cross this line or not at some point, then we just have to set them equal to each other. And then we solve the equation, okay? So let's see. So negative 4x squared plus 5x minus 1 equals negative 4 times square plus 2. So let's clear the parentheses on the right hand side. So negative 4x squared minus 8. So we can see that the negative 4x squared, they cancel each other. So we are left with 5x minus 1 equals negative 8. So we have that 5x is negative 7. So x equals negative 7 over 5. Okay, so we found a solution. So that means that we are going to cross the horizontal line. The horizontal asymptote y equals negative 4. We're going to cross it. And this is going to happen when x is negative 7 over 5. So what's the conclusion here? So yes, the function out of x, so out of x will cross the horizontal asymptote y equals negative 4 at the point. So what's the point that we're going to cross it at? We're going to cross it at the point negative 7 over 5, comma, what's the y value of the point? Can anybody tell me what's the y value? Should be able to tell me pretty quickly. What's the y value of this point? Negative 4, very good. Remember, we are negative 4. Remember that we are crossing the horizontal asymptote, so the y is fixed, it's negative 4. What we didn't know is we're going to have an x. Yes, we do, negative 7 over 5. So whenever you graph this function, you have to make sure that this point, we are crossing the horizontal asymptote. Okay, questions? Okay, so let's look at the next one. So we have p of x equals 3x minus 1 over 2x plus 7. And remember that here we had horizontal asymptote, and it was the line y equals 3/2. Okay, so again, if we want to know whether we're going to cross this line or not, we should just set them equal to each other. Okay, and then let's solve. So remember, this is a proportion, and all we do is here we cross multiply. So this is 2 times 3x minus 1. This must be equal to 3 times 2x plus 7. And now we solve. So we get 6x minus 2 equals 6x plus 21. We already see something fishy here. The 6x cancel out, so we get the statement that negative 2 equals 21. And this is certainly a false statement. So what does that mean? It means that this equation right here have no solution. So P of x will not cross the horizontal asymptote. It's not gonna cross its horizontal asymptote. Okay, questions for number 3? All right, perfect. And then let's look at number 4. We had our slant asymptote. So we have g of x equals negative 2x squared minus 3x plus 7 over x plus 3. And then here we found slant. It was y equals negative 2x plus 3. All right, so let's see if we're going to cross it. So just move the x plus 3 to the other side. We get negative 2x plus 3 times x plus 3. Clearing parentheses on the right hand side. We're going to have negative 2x squared minus 6x plus 3x plus 9. So we see that these negative 2's are gone. So we get negative 3x plus 7 equals negative 3x plus 9. Again, the negative 3x's are gone. So we have statement 7 equals to 9. So the Sarah, negative 2x plus 3, that's a slant asymptote. That was, remember, we are working with the same functions that we work with above. So this was example number 4, right? And we figured out that this function had a slant asymptote, no horizontal asymptote, and the slant asymptote is negative 2x plus 3. You okay? So the question that we're trying to answer is to determine whether our function crosses the horizontal or slant asymptote, if it has any. Okay? So in this case, this function number 4, the function g, it has no horizontal asymptote, so we don't have to worry about that, but it has a slant asymptote. So we are trying to figure out whether we're going to cross that line or not. Oh, the negative 2x plus 3 by division. We did that above in number 4. I mean, look at the screen. Right? That's you divide the top with the bottom. We did that and we got negative 2x plus 3. Yes, in this case we did synthetic division because it was easy because x plus 3 is, you know, the nice device. Okay, no problem. All right, so we are here trying to figure out whether we're crossing that slant asymptote or not. But, you know, it turns out that we get this statement, 7 equals to 9. Once again, it makes no sense. This is false. And what does this mean? Well, it means that this equation has no solution. It's not a solution. In other words, the function g of x will not cross its slant asymptote. So g of x will not cross its slant asymptote. Okay, question. So, okay, so are you okay, honey? All right. Okay. Yeah, the negative 6x got combined with the positive 3x, giving you negative 3x. And then it got canceled with the negative 3x from the other side. That's what happened there.